All right, so I up until now I haven't really been a stickler on tests and using notes and stuff like that. But I was recently talking to Mrs. Ensley, our esteemed department chairperson and AP environmental science teacher. Who you guys have environmental science, some of you, right?
Yeah.
So we're going to be modeling our test procedures after hers. Oh, why did you say, oh my gosh? Because now you can't use your notes on tests?
No, just the way she does things. Like, I don't know if like
live quests or better test notes.
Yeah, but they're not a real test. It's not preparing you for the AP exam. That's why we need to start. So good. Oh, come on. This keyboard.
her tests are fine, but like some of the other stuff she does.
You know you're on recording right now, right?
Who's recording?
I am. Probably can't hear you though. Okay, our Gauss's law test will be next week. Notice it says Gauss's law, not simple harmonic motion. We'll be using a very different format for this one, and we'll do so for all tests that follow. But it's going to be curved. I mean, there's going to be curved probably on the test, if needed. And so it's not like you're still going to get a grade assigned based on your performance as compared to your peers. I'm borrowing a procedure used by our biology, AP, environmental science teacher, and science department chairperson, Mrs. Ensley, that is designed to ensure equity for face-to-face and online learners. From now on, tests will not be open notes, and so certain procedures will need to be followed. Most importantly, online students will need to take the test during their scheduled class period. That's all you at home that aren't on Zoom right now. Most importantly, online students will need to take the test. I already said that. Other instructions are at the end of today's module. Please read them, download the AP Classroom Lockdown browser. That must be done. And ensure that you're ready on test day. What day that is, not quite sure yet because I do want to have a quick run through to make sure this will actually work the day before. So next week we'll spend a day reviewing for the test and testing the new procedures before we actually take the test. Please note, online students that do not take the test according to these procedures will receive a 0 for the exam and will need to do the retake. There will be a retake for a maximum of 70. Students that fail will also be able to do a retake for a maximum of 70. I'll have a retake scheduled for this one. Okay, so if you're not in AP Environmental Science, then pay attention. Your test over Gauss's law and electric fields will be next week. For face-to-face students, that's you guys, in case you didn't know. Your exam will take place during your class period. When you arrive at class, sit in your usual assigned seat, but move the chair to the front so you're facing the back of the classroom for obvious reasons. Turn off your cell phone and place it in your bag and your bag on the floor. You may only have your device and a calculator at your desk and a formula sheet, which I will have a set of formula sheets that you will then be able to keep. If you're on a district-owned Chromebook, before you log in, you select the Apps button at the bottom of the screen, again prior to logging in. Then select the College Board app and log into AP Classroom. You'll automatically be in AP Classroom with the lockdown browser active. If you're on your own device, you will log into AP Classroom, go to your assignments, and when you open your exam, the lockdown browser will open. You have to have the lockdown browser installed, though. So it is essential that you have the lockdown browser loaded and checked prior to your exam time. Again, it's essential that you have the lockdown browser downloaded and checked prior to your exam time. There's nice instructions for downloading the lockdown browser if you need to. You may not use your phone, the internet, or notes on the exam. I will be watching, and the lockdown browser will notify me of any suspicious activity, and I'll be able to see your guys' computer screens. If you guys are online learners, which is none of you, but all of you, you will need to log into Zoom and the lockdown browser to take the exam. Both of them. Please be logged into the Zoom meeting. A link will be posted on next week's testing page in Canvas at least 5 minutes prior to the exam start time. If necessary, you may prop your phone and Zoom on it. It is unlikely that you'll be able to have the Zoom tab open at the same time as the lockdown browser. So you can use your mobile device, Zoom from there, put it on your pop socket or whatever you're using, face it towards your face, and then open the test from your computer. If you need a computer, let me know, and I will contact Ms. Magana and see what we can do about Chromebooks. If you have your own Chromebook, by the way, this ain't gonna work. The the lockdown browser does not work on your personal Chromebooks because it's Google and because Google and AP Classroom, or I don't know why. It's silly. But if you're in that case, if you do all your school stuff on your own Chromebook, you need to let me know so we can get you a school-provided Chromebook. Okay. So you're going to have, online students probably going to have 2 devices unless for some reason you can open Zoom and the lockdown browser at the same time. If you're not on Zoom with your camera and sound on for the entirety of the exam, your exam will not be scored, meaning you get a 0. What that means is that, first of all, so you know, the people in my classroom will not be able to see you. I'll have it on my laptop pointing towards me. They won't be able to hear whatever's going on, but I will because I'll have headphones in. So you have to have your Zoom camera, you have to have your camera on and your sound on. And that's so I can make sure you're not shuffling papers and looking through notes and looking at other computer screens. So yeah. If you're on a district-owned Chromebook, you'll need to select the apps button, blah, blah, blah. I already went over that. Same thing. Download, lockdown browser download instructions. You may not use your phone, the internet, or notes on the exam I will be watching. The lockdown browser will notify me of any suspicious activity. All right. So again, we're going to have a brief mock run-through of that before the actual test next week. This is mainly for online students because you're the one that's going to have Zoom open and AP Classroom open at the same time. All right. That being said, let me go over a problem that might help you with the quest assignment. Some of the questions on the quest assignment. Let's say we have a charged insulating sphere with total charge 2Q, positive 2Q, it's positive charge, and it's surrounded by a charged conducting shell, and that charge is negative. Negative Q, not 2Q, just negative Q. Okay. Part A, plot the electric field as a function of radial distance R. Sketch, I should say sketch. I should say sketch. All right, within the Gaussian sphere, and I assume all of you have watched those videos now. If you watch the videos, then you know that up until we get to R1, the electric field varies linearly with distance, right? It varies linearly, and I don't remember off the top of my head, but on the inside of a charged insulating sphere. Do I have that? Oh. It is linear. Watch the video and you'll see. The electric field varies from 0 because there's 0 charge enclosed in the infinitesimally small Gaussian sphere centered on the origin. And so it climbs up linearly until you get to R1. When I get to R1, an infinitesimally small distance away from R1, the inner charge just acts like a charged point charge, right? A point charge with charge 2Q. And if I'm outside that, then it's just good old KQ over R squared, right? So in this case, it would be 2 KQ over R squared. Capital R squared. Because now, R1 squared, sorry. Because now right outside, an infinitesimally small distance outside of that surface, I am now enclosing charge 2Q. And so Gauss's law, or just the definition of electric fields, gives us that value for the electric field. Outside of that, as I go from R1 to R2 inner, that's why it's an I, R2 comma I for inner surface of R2. As I go from R1 to R2 inner, it's going to fall off according to the inverse square law, right? The electric field is KQ over R squared. And so it's going to fall off according to an inverse square law. So it'll look something like this. And then we get to somewhere. It's still going down. Okay. So this is proportional to 1 over R squared. where R is this green R right here. What's the electric field in here? And the reason, by the way, is if I draw a Gaussian sphere around here at any point between those two, between R1 and R2 inner, then it's enclosing charge 2Q, right? And so the electric field is K times 2Q over R, little r squared. What's the electric field in here?
Is it a conducting?
It's surrounded by a charged conducting shell.
Zero.
Zero. It's a conductor at 0. So you can know that and you can plot that. It is 0. Let's say this hasn't quite fallen off by that much. So then this is a discontinuity, right? Graphically. Which is fine. This is a discontinuity. You have an abrupt change in the physics. So what about outside of R2 outside? We just draw a Gaussian surface there. So I have a new R. How much charge is being enclosed by that Gaussian surface?
Negative KQ over R squared.
Negative?
It's a negative charge, yeah. Isn't it?
How much charge is enclosed within that Gaussian sphere?
Q.
Positive Q. And I have 2Q and I have negative Q. So total charge is just Q. 1Q here is negated by that negative Q. Okay, it doesn't matter where the charge is inside a Gaussian surface. You just add it up. The charge here, you add it all up, you just get KQ over R squared. And so it will fall off. You'll have another inverse square proportion falling off there. So that'll be proportional to, again, 1 over R squared. But now I have less charge, right? So something like that. That's a quick, brief sketch of the situation. Sorry, I can't talk today. Wish it was Friday. Okay. Now, questions like this tend to give students some trouble. And I know I haven't gone over a question like, so I'm going to go over it. What is the areal charge density on the inner surface of the conducting sphere? Charge density, this is sigma because it's area, is charge per unit area in general. How much charge is on the inner surface of that conducting shell? We can know exactly how much. No. Think about Gauss, a Gaussian surface. Let me erase this one so it's not as cluttered. Now you have to trust that Gauss's law works. Hopefully you trust that at this point. Because we have showed that we can use Gauss's law to come to the same conclusions that we came to when we did much more rigorous mathematical stuff. So if we trust Gauss's law, and we draw a Gaussian surface within the conducting shell, and we know the electric field within that conducting shell is 0, then the integral, closed loop integral of E dot dA has to be the enclosed charge divided by epsilon naught. The only way that the electric field can be 0 is if the enclosed charge is 0. Right? Because here if the enclosed charge is 0, then the electric field ends up being 0. Right? It's easy to see that. So how much charge is enclosed by this Gaussian surface?
1.5.
You're overthinking it. How much total charge is enclosed by this Gaussian surface if the electric field there is 0? Close? Now, how much total charge is enclosed by the Gaussian surface if the electric field is 0? the electric field is 0.
0.
0.
But isn't there still 2Q on the inside then?
Not 2Q, but if there's 0 charge, 0 net charge enclosed in this surface, but I know there's 2Q here, how much charge must be on the inner surface here?
Negative 2Q.
Negative 2Q. Right? And you might say, well, there's only negative Q here. Well, then what does that tell me about the outer surface? How much charge is on the outer surface? 1Q. That's okay. That's okay as long as it's evenly distributed. Right? It's okay. Remember when you have corners and stuff, the charge surface charge density is not the same. So if the electric field within the conductor is 0, then that means I must have a bunch. I'll draw them in red. I must have a bunch of negative charge that has, because of the charge configuration here in the associated electric fields, migrated to the inner surface in order to negate any electric field that would exist within the conductor. How much charge is that? That's negative 2Q. How do I know that? Because that Gaussian surface must enclose 0 net charge. So this 2Q must be negated by a negative 2Q on that inner surface. But if the conducting shell has a total charge of positive Q, and I have negative 2Q on the inner surface, that means some of those electrons must have left the surface. Or at least you have electrons leaving here, coming towards the inner surface, leaving a net positive charge on the outer surface. So I would have positive charges on the outside, but I would have half as many. Again, if you don't trust Gauss's law, then this isn't obvious, right? If you trust Gauss's law, then this, I won't say is obvious, but it's logically must be true, okay? Notice I've drawn half as many, right? Because on the outer surface, I just have plus Q, which gives me a total charge on that outer conductor of negative Q, right? Which we're told we have. So charge density then, is on the inner surface, is negative Q. That's the charge divided by the area. Well, that's just the surface area of a sphere with the radius R2 initial. So it's just negative Q over pi. No, that's area of a circle. Area of a sphere, 4 pi times.
Wait, didn't you say it was negative 2Q on the inner surface?
Yes. There's a 2 there. You didn't see it? See, it's right there. Sorry about that. Yes, you're correct. Negative 2Q over the area of that spherical shell, which is just 4 pi times r squared. In this case, it's r2 inner squared. And then you can simplify that, obviously. It's just negative Q over 2 pi r2 initial squared. So that would be your charge density for the inner surface. And you can do the same for the outer surface, but the key there is the Gaussian surface. If a Gaussian surface encloses 0, or if there's an electric field within a conductor, the electric field is always 0. If you draw a Gaussian surface within that conductor, whether it's a shell that's enclosing another charged object, doesn't matter. If the electric field within that conductor is 0, then the total charge enclosed by a Gaussian surface that is drawn within that conductor must be 0. The total charge must be 0. Enclosed, charge enclosed. If that means that charges have to move around in the conductor in order to create that scenario, to create to make that happen, then that's what they do. Right? Charges can move in conductors. That's the whole idea. That's why we got electricity, because electrons can move through conducting objects. If they couldn't, then your life wouldn't be possible. Any questions, comments, concerns? All right, rest of the period you can use to work on the quest assignment. Goodbye, people at home.